Okay, hello, welcome back. So today we're going to switch gears a little bit. We just understood renormalization and loops. We're now going to build something different. We're going to understand how global symmetries work in the functional formalism. You've already studied global symmetries once, and you know they give you conserved currents. Today we're going to develop that a bit more from the point of view of the path integral. Okay, so let me give you an example of a global symmetry. An example of a global symmetry is, for example, the complex scalar field. So consider the theory that depends on phi and phi dagger, defines a complex scalar field, and consider the following action. D phi dagger d phi minus m square phi dagger phi. Okay. So this theory is clearly invariant under phase rotations of the scalar field. So it's invariant under phi goes to phi times an arbitrary phase, I alpha. And you can write this in an infinitesimal form. The infinitesimal form of this transformation is that delta phi equals to I alpha times phi. So this is infinitesimal if alpha is much, much smaller than 1. And clearly, this phase rotation leaves this action invariant. Okay, so this is a simple example of a what's called a U1 global symmetry. So in this lecture, I'm going to be a bit more general. I'm going to consider instead a theory with a bunch of fields. Phi A, where A runs over some number of fields. And I'm going to imagine that the action of this theory is invariant under a more general global symmetry. So I'm going to take my general global symmetry to be of the form phi A of x goes to phi A of x plus epsilon times delta phi A of x. And this is some sort of general transformation. I've not told you exactly what this transformation is, but it's some general transformation of the fields. And I'm assuming the action is invariant under this. So what that means is that if I compute the action on this field configuration, it is equal to the action on the untransformed field configuration. Okay. So this is what I'm going to study from now on. So, and also, it's maybe good to keep in mind the example of the complex scalar field as a concrete example of the things that I'm discussing. So the first thing I want to do is review the classical Noethers theorem in maybe slightly different language from how you've seen it before. So, as you're all well aware, global symmetries lead to conserved currents. And the connection between these two things is given by Noether's theorem. I want to review how this works. Okay. So first, let me consider the following thing. Let me consider this variation, which I'll call star from now on. I want to consider star with a symmetry parameter epsilon. Remember, epsilon was the symmetry parameter here. The symmetry parameter epsilon that depends on x. Okay, so I'm going to consider epsilon of x, where x is the space-time coordinate. So my new transformation is phi a goes to phi a. So here, phi a is a function of x. Phi a goes to phi a of x plus epsilon of x delta phi a of x. Okay. So no matter what it looks like, some of you might think this has to do with something called gauge symmetry. This has nothing to do with gauge symmetry, okay? Because we have not discussed gauge symmetry yet. So this is just a thing that I'm doing, all right? Now, this is not a symmetry of the theory, okay? Because, you know, the whole point of a global symmetry is that you need the symmetry parameter to be constant. That's almost the meaning of a global symmetry. That's why it's called global. And so this is not a symmetry of the theory. The theory is not invariant under this. And particularly that means the action will change, okay? However, it is invariant if epsilon is constant. And what that means is the variation of the action must be proportional to a derivative of epsilon. Because that variation has to vanish when epsilon is constant. So in particular, what this implies is that the variation of the theory under this transformation must take the form d4x j mu of x d mu epsilon of x. Okay? So this is the most general form of the variation that's consistent with everything that we've done. And technically, I'm actually using locality here in making this statement, where by locality, I mean that the action is the integral of a local Lagrangian density, L. All right? That implies that if the variation of the action is proportional to the derivative of epsilon, it must take the form of the integral of something dotted into that derivative. So notice that this is really the definition of J mu. Okay? J mu, which we'll see, of course, is going to be conserved, is something dotted into d mu epsilon. Okay? It's the thing that appears when you do this. Okay. Now, let me point out that I can integrate by parts on this, and I find that this is equal to times epsilon of x. Okay, where here I've done an integral by parts. And as usual, ignored all the boundary terms. Okay? Okay, now, is this 0? I mean, no, it's not. I mean, why would it be? There's no reason for it to be 0. Okay? Remember, the theory is not invariant under this weird manipulation that I'm doing. So, but why am I doing this? Well, I want you to now consider, imagine that phi obeys the equations of motion of the theory. This lingo is sometimes called on-shell. On-shell means obeying the equations of motion of the theory. In that case, the variation of the action under all variations of the fields vanishes. That's the definition of something obeying the equations of motion. In particular, this is true for all variations. And in particular, it's also true for this particular variation, which is arising from the symmetry transformation. So in that case, if phi obeys the equations of motion, then it's true that the integral d4x epsilon of x equals to 0. And in particular, because this holds for every epsilon, this implies that d mu j mu of x equals to 0. Okay. So notice that we used two things. We used the fact that the action was invariant under the global symmetry when epsilon is constant, and we used the fact that phi was satisfying the equations of motion. Another way to say this is the current is conserved classically when phi a satisfies its equation of motion. Okay, so this is a slight rephrasing of the usual Noether's theorem. So this also, by the way, gives you a way to compute J. Okay, so if you want to compute the current J, what you should do is vary the action by a time and space varying symmetry parameter, and you'll see you can always write it in this form. Pick out the piece that is proportional to d mu of epsilon, and that's J. Okay. So I should just stress that this also gives you an algorithm to compute J, as well as proving that J is conserved. Okay, so that's all fine for the classical theory. Now we want to understand what happens when we stick this into a path integral, and that's what we're going to do next.